So self-inductance, a coil is connected to the battery and key. So it's a battery, it's connected with the key. Now the key is open. So the key is connected, the current flow through the coil, a magnetic field is produced. Already you know that. So when current flow through the coil, an EMF, a magnetic field is produced. That's the magnetic lines of force. Okay, so according to the Faraday's law, a magnetic field is produced. When the current is flowing through the coil, magnetic field is produced like this. It is passing through the only axis of the coil. So the magnetic produced from the coil, that is pi b. N is a number of turns that is directly proportional to the flow of current in the circuit. So the magnetic field produced in the coil is directly proportional to the flow of current. So equating that equation, you have to multiply the constant L. So N pi b equal to L into I, where L is the self-inductance. That is called the constant self-inductance of the coil. So L is the self-inductance of the coil, that's constant. You multiply by the equation. Or you can write that coefficient of self-inductance of the coil. That L is called the coefficient of self-inductance of the coil. Right? Okay. Then, so N pi b. Pi b is the magnetic flux. N is the number of turns. So d by dt of N into pi. So we are differentiating on both sides. So differentiating on both sides, you can take in that equation 2. So after differentiating this value, you will get, so according to the Faraday's law, E equal to minus d n pi by dt. So this is Faraday's law. Already you know that Faraday's second law. So you can take in that equation is a 3. So here, comparing these two equations, so you can write like this. Induced EMF E equal to minus L into di by dt. So comparing that equation on both right side. So E equal to minus L di by dt. That is the induced EMF produced in the coil. The EMF is induced. See here, when the current flow through the coil, an EMF is induced. That induced EMF E is equal to minus L di by dt. The induced EMF opposes the flow of current in the coil. See, when the current is flowing through the coil, an EMF is induced. After the magnetic field is induced, what will happen? This is the magnetic lines of force. These lines of force is cut by the coil, this coil. So, an EMF is induced inside the coil again. That induced EMF value is equal to E equal to minus L into di by dt. That induced EMF opposes the flow of current in the coil. That is called self-inductance. So, this current flow ஆகிறதுனால இதுல magnetic flux produce ஆகுது. இப்படி magnetic flux produce ஆகிறதுனால the magnetic lines of force is cut by this coil. So, cut by the coil என்ன ஆகும்? According to the Faraday's law, EMF is induced. The induced EMF is opposite direction to the flow of current in the coil. So, it opposes the flow of current in the coil. அப்ப என்ன பண்றது? coil currentல flow ஆகும்போது என்ன பண்ணுவோம்? Opposite ஒரு current induce ஆகி இதை தடுக்குது. That is called self-inductance. So that value is equal to minus L into di by dt. Okay. So this is the equation according to the Faraday's law, E equal to minus d by dt of N pi b. That is equation number 3 according to the Faraday's law. So EMF is induced in the coil. So it's the final equation that induced EMF in the opposite direction due to that the flow of current in the opposite direction. Okay, that current is opposite direction. Flow current opposes the flow of current. That is called self-inductance. That is shown in that equation E equal to minus L into di by dt. So where L is the self-inductance, I is the flow of current. So here we can define that self-inductance in a Henry. So here now you are going to see the amount of work done. So amount of work done equal to, you know, that force into displacement. So dt is கீழே கொண்டு வந்த dt அந்த பக்கம் இருந்தது. So dw equal to dw by dt equal to em of E into I. So amount of work done dw by dt equal to Li di by dt. We are substituting that value here, that instead of E. So you can get this equation. So the negative sign indicates the flow of current. So the negative, the not necessary to write the negative sign here. So dw is here. We have to get the w. So integrating on both sides. So dt cancel each other. So integral of dw, integral of Li dt from 0 to I. So integrating that value, you will get w equal to 1 by 2, that is I, x into dx, x square by 2, that formula. So 1 by 2 L I square, that is the amount of energy stored in the coil. That is the amount of energy stored in the coil. So that is equal to E equal to half mv square. That's for the kinetic energy. So we can compare the two equations. So it is a kinetic energy equation. So like that here, that m is equal to that L. L means that is moment of inertia. That is mass in that equation E. Here L is the self-inductance. They are doing the same work. So m is the mass of the particle. Due to that, that kinetic energy is defined as E equal to half mv square. Next thing is self-inductance of a long solenoid. So now we are going to take the very long solenoid. So now we are going to calculate the self-inductance of a long solenoid. So taken as the length of the coil is L, the cross-sectional area is A, and the number of turns, n turns are there. So n is equal to n by L. Or you can write capital N equal to small n into L. Okay, you can write like that also. So here the length of the conductor is L. So magnetic induction produced by the coil, you know that B equal to mu naught Ni. Already we derived the equation. So magnetic induction produced by the coil B equal to mu naught Ni. So that is the magnetic induction produced in the coil when current flow through the coil. So now we have to calculate the self-inductance of a long solenoid. So B equal to mu naught Ni. Mu naught is the permeability. N is the number of turns. L is the current. So magnetic induction produced in the coil by B equal to Ba. So cos theta becomes 0. That's why Ba is here. So pi B equal to Ba. So Ba is the total magnetic flux produced by the coil. Now you can write N pi B. So N into pi B. Number of turns is multiplying on both sides. So N equal to, you can know that value, substituting the B value. So you will get this equation. So N pi B equal to mu naught N square Al into I. Okay. So this is the final equation. In this equation, N pi B equal to L into I. Already we calculated that. So comparing these two equations, that is equation number 9 and that equation, finally we will get self-inductance L is equal to mu naught N square Al, because I cancel. So remaining value mu naught N square Al you will get. That is the self-inductance of a long solenoid. So this is the value of self-inductance of long solenoid. So suppose it is placed in a different permeability. If filled with another permeability, you can write mu naught mu r N square Al. Instead of mu naught, you can write mu r. So that is relative permeability. So placing in a different medium. So you can write self-inductance L equal to mu r mu naught N square Al. Instead of A, you can write pi r square also. So pi r square, suppose it's a circumference, you can write pi r square. So from that you can calculate that radius of the coil out. You know all other values. So that's a self-inductance of a long solenoid. Okay. So next we are going to see that this is the self-inductance of a coil.